Good evening, everyone. I would be talking about a project called PizzaDB. Now, this project might seem like a joke to you because of the name, of course, but the name came from a very particular choice of food and has no particular meaning in general. So, that's the whole point of PizzaDB. That I made it because I was interested in something, and it is named after something I am interested in. So basically, that's the point. Now, let's talk about how it works and how it actually functions as a database. So basically, in PizzaDB, what happens is PizzaDB is consisting of three layers. Okay, in three layers, those three are first of all the consensus layer. So consensus layer, the other one is storage layer, and the third one is a network layer. So these three layers work together to make this particular database functional. Now, what exactly this database is? This database is basically distributed fault tolerant database, and it's a key value store, not a relational database. It only stores a key and a value in a very particular way, which is different from many other databases which use B trees, B plus trees, and here we are using LSM trees. So how it works, let's find out. So let me first explain you what are the three layers of of this database. The database consists of the first a consensus layer. Okay, this consensus layer is responsible for you know uh, to actually decide on what data to commit. Okay, in the database. All right, so when a data line or a key value pair or just a value is sent to the database, that database actually does not have the authority on its own. At the single node does not have authority on its own to append it to the db file directly. So what it does is, uh, on the first port where it's reached, the file which is the leader actually takes it as an uncommitted log, and that uncommitted log is then ran and broadcasted to the other nodes. These other nodes, what they do is they use a consensus algorithm, and they decide if we are going to append this and commit this into the final database file .db file, which is this. These are the .db files for all the three ports I have. This basically runs on three consensus, and we can make it for multiple also. So this is how it works. Now, what are we going to do in this entire project? Then the second layer comes along with this. Now, this project has an engine working for the storage, of course, and the storage is, of course, a very important aspect of this project because it is different than how we usually store here. So the difference here is we have O1 logs. How it performs O1 logs is a very big question that comes to mind. So we are following a Bitcask type of data structure to store the key value pair first of all, and take it like a journal. Okay, for example, a accountant's journal, or accountant is writing logs somewhere for a value and a key. It has a key means a serial number for that log. In the analogy where an accountant is writing uh, a log for any purchase or any transaction, so that transaction log has a key which is serial number. In that analogy, here it can be anything. So that key is basically stored, and also stored in another part which is called a key directory. So that key directory stores that where that key exactly is and what that key contains, but it does not contain the value. That key directory does not contain the value. So how it works now, in normal databases, when we have to update something, the update goes through a process called traversal. Okay, you have to traverse through a entire b or b plus tree, and that tree is then it allows us to find that particular key and that value, and for that key we update that value. That's how it basically works in general cases in traditional databases. Now, in this database, which is actually quite similar to many other modern databases which are being used, which are very fast, and which are fault tolerant. So this database, what it does is it can append the data, the key value pair, in the latest entry. Okay, it basically appends it at the last. It does not traverse through the entire list, cannot write. There's only read all for the already appended, already committed data. That's the only thing you can read. Okay, you cannot update them, you can only read them. Now for the same key, if that key exists, it uses that key and writes another tuple, or say a key value pair at the end of the database. And what it does is, we know the key, we know the new value, the key directory knows that the new value is there, and the key directory will always point to the latest entry where where that key was mentioned, that particular key was mentioned. So that's how it works. And you might be thinking that data will pile up in the memory, and how will it work in RAM? It basically does not work in RAM. It gets shifted to the disk at the point where like we know that if the system crashes or something happens, then RAM is not a reliable memory, so it pushes that to the disk. And that's a drawback, or say we have to compromise here for that. So that's how it basically works, the storage engine works. Now so we are clear with the storage engine, which only allows append only writes. Now the network layer. Now the network layer has a custom TCP protocol. Why TCP? This TCP protocol is there because in general we use port get and others from the servers. That actually allows us to get the entire data, but in packets. Okay, HTTP packets, and that packets are large, could be you know could be taking space, could be taking latent, could be causing latency in network because of that heavy transfer, because the amount of bits, or the data in general is going to be large if we send an entire packet, right? So what it does is, it's just uses TCP to send raw binary for the packet, or say a key value pair. It only has a key value, so it sends the raw binary. Now here you might say that this is a user's drawback and can be improved. Now this is a very good point, but the problem is this was just a project, and was not, I did not plan it to go this far, and this is one of the future things I'm going to add into it, and how we are going to change it. If I have to change it to HTTP, I will surely do that. So that's the network layer. So let's discuss the entire process, how it goes through. Now let's see. You can see this is a flow diagram for this. Now the client app actually uses TCP, and then it sends a data key value pair to the TCP server. Okay. Now that TCP server, what it does, it converts that the key value pair into raw binary or bytes. In bytes, it is sent directly to the protocol parser. Now the protocol parser contains a file called pizzaql.go. This is just just a name I got for the set get delete ping authorization function. I did not intend it to be called pizzaql. It just came into my mind, and it's called that way now. Yeah. The Back to the architecture diagram. Now here we can see is it goes to the protocol parser with header and the body. Header is basically key, and the body. Now what we are going to do is, there are two choices we are here. Okay, we have two choices here. What are the two choices here? So either this already exists, and this this protocol is asking for us to get a value. So if we go for get a value, we send this request to the DB controller. This DB controller finds the data here in the DB file. First it checks the key directory, and then it finds the DB file for the particular key, and returns the response directly to the TCP server. So this is the get thing. There's no other thing to be discussed here. Now in the handle set or call propose function, what it does is, it goes through this and actually gives a temporary write to the Raft core, or say the leader state. The leader is one of the nodes which actually decides uh, uh, the which actually makes the appends, and it's the thing is the entire process goes through a consensus where there should be a voting on everything. So now, for example, there we got a value and we got that value here, and that value is now an uncommitted write. It is not committed yet, so we will broadcast it to the other nodes. The other nodes will receive the broadcast, and there would be an just like that broadcast node will return a value that, yeah, okay, sure, we can write it now. So the vote will be here, the vote will come back, and as long as the vote will come as soon as the vote will come back, it will append it directly to the Raft log. All right. Okay. uh, okay, I'm sorry. That I'm completely sorry. It will append it to the Raft log first. This is the temporary storage we have for the uncommitted logs. That uncommitted log will be checked with the other nodes. Those nodes will vote, and as soon as the consensus is reached, the committed log is pushed. Now it is pushed to the committal loop. This is a go routine. This makes it concurrent, and we need concurrency in this process because uh, that will make it more fault tolerant as a distributed database. Now, the next thing that happens is we send it to the DB controller, and that DB controller knows that we have to encode and append the data. This encode and append the data directly writes it to the port file. So that particular port has a DB file. That port file will contain the data. Now, also what happens is we have different port files, as you can see here, .db. Now it doesn't necessarily mean the data can will be in all of them. So the problem is, how do we find it? So of course the offset and the value, key value, and where the the address of the data is found in the key directory index. So that's how it helps us to find the entire data and also write it there. So that's how it basically works. I can go into the code parts, but this that those are not really necessary because um, those are not those are used from older snippets, and I have also used a little bit of AI to write the code. But the entire uh, the entire project, from Raft consensus and to the Bitcask, those storage and the consensus algorithms that I have written, those are inspired from two papers. One of them is just uh, kind of a report on Bitcask, and second one is a complete paper written by two students in Stanford. Now, that's a very old paper, although, but Raft works, and it's much better than Paxos in general. So this was my entire project. Now we can actually take a demo for this. I have this terminal ready here, and I have also taken in account that I often forget the commands that I have to run. So I have copied them here, and I'm going to use that. I think I'll have to open two more instances of my terminal. This is a WSL terminal, you might know that. Let me, okay, the first one is running perfectly fine. This is good, this is great. Now let's just do this cd db def and ls cd pizza db. I'm sorry for the delay. um, cd db dev slash pizza. Okay, so I'm really sorry for the delay. Now we need two more nodes here. So what we will do is we will I'm sorry we will put these two nodes. Now The one running on 8001 and its peers are 2 and 3. Now this one is going to run on 2 and the peers are going to be other 2. So this is running. Alright. It won the election. Okay. Now let's go for the next one. How would we go for the next one? Now this is the third node here. Okay, everything is going on. The pizza QL gateway is available and the server is listening on 9003. On 9002, its server exists on 9002, and this is the leader because only two of them were here. It was campaigning before these two even existed. So now if they were running in parallel, it would have been a different approach here. So yeah, that's it. So now let's see. Let's go for another of our terminals. I'm sorry, this is actually just a show for me. cd db dev slash pizza db. Okay, so what we are going to do is we are going to run the chaos.go file. Now what this will do is it will continuously add and try to crash the entire server. So okay, wait, client cd client ls. Okay, go run main.go. Alright, this got us a very good result. So we committed to the disk that this hero Batman is set, and they also agreed to this. You can see here, right? Now we are going to use a chaos script. Chaos, sorry, ls cd chaos, and let's see, yeah, go run main.go. So it is going to write in a very good speed here, and it's trying to crash it. Alright, now this is writing it continuously. Now we are going to crash one of them. Which one we are going to crash? We are going to crash the leader, of course, so that we have a new leader. We crash the leader. Alright, now they are still writing. How are they still writing? Because this one is the leader. Let us close this. Now we can see that somewhere here we got an election campaign here. Yeah, okay, it campaigned and won the election. Okay, so that's why it became the leader, and it followed it, and the data was appended here. So this was working perfectly fine with the go routines, and we can see everything going perfectly well. Okay, now let's check the logs, check all the logs we need, and we will be done. Okay, sorry. Okay, it passed. What actually it did is it tested if we can recover the last 10k entries. So it obviously can, because this was built that way. And not just 10k, actually it is an underestimated statement. It can actually go for 25 times more. So basically it's 250,000 writes, and that's a very big number for a normal college project. Concurrent go routines completed without race conditions. So that also is tested perfectly fine. And now we are going to do is let me check the benchmarks for each. Yeah, so these are the benchmarks. Okay, this is still running. We can close it. Yeah, you can see these three are perfectly running fine, and this is actually a very great way to represent this. all of the benchmarks are passed. This is great. This is absolutely perfect. So you can see this project works as intended, and this is something I made last year, and I was expecting it to be just a project just for fun, to learn more, and it grew and grew and grew, and it came up to me to this point that I can actually use this for my own projects. Although I haven't, and I'm still going on to building a complete web interface for users to use it through tokens, and that will soon be completed as soon as I can. I also have the code files for that. Uh, Here we go. CD pizza db dash web. This is the entire package here. So this is entirely completed, and I hope the project was meaningful for the company, for Couchbase, and I would love to be a part of Couchbase as much as was excited to build this project. And this project also, I consider that it matches the work culture, work functions, and everything that we do, that you guys do at Couchbase, and that is something I want to be part of, and I am very excited to be a part of. Thank you so much.